Hello everyone. Today we have advanced dimensionality reductions collabs. So we have three different collabs. One is for the image data set, other one is for tabular data set, and other one was run on Databricks and downloaded the Jupyter Notebook file, and then I am using Colab to demonstrate that. So let's begin with image data set one. So what I have done here is I've imported the sklearn data sets and I have used the Olivetti Faces app. Let's try to load that data set. In this cell, we will be loading it, and then I will plot the data set. So this is how it's looking like. We have 40 labels, and I've randomized some labels, and this is how it looks like. The shape is 400 to 4096. We have these many images, and let's go to the next part. So we'll begin with randomized PCA, and this is the code we have applied, and we'll visualize the randomized PCA as well. So we'll just use randomized PCA.fit function and transform on X. So it will take two PCA principal components, and it will plot the data, and it will get the cluster by itself. It is the algorithm working behind is randomized PCA, and since it is a high order data set, it is not working as efficient as possible. Now, next we have TSNE for linear dimensionality reduction. It is also a powerful nonlinear DR technique, particularly effective for visualizing high dimensional data set like this one. So we'll see. So we have some clusters over here, which it is identifying some really good clusters. If we see, we have these as cluster, this as cluster, and we have some really nice visualization of different clusters. So now we'll be applying visualized UMAP. So for that, we'll install UMAP learn, and in the next, we'll just uh, use UMAP dot all caps UMAP, and then we'll call the UMAP model.fill function, and then we'll try to visualize the UMAP results. So this is how it looks like, not better than TSNE, but still good enough than PCA. Randomized. Now we'll apply isomap, and this is the isometric mapping. It is again the nonlinear dimensionality reduction technique that preserve geodesic distances between points and make it. This also helps us make useful for database with curved manifold structure. So this is not, I think, good for an image data set like we have, but still good enough than randomized PCA. So now we'll be applying visualize kernel PCA, and for that again we'll call this kernel PCA.fit function, and then we'll use visualization. So visualizing this shows that the clusters are not that distinctive, and it is not performing well. Um, so now we'll be applying incremental PCA and visualize. So incremental PCA is not giving us a good result. The TSNE was, I feel, stands the best so far. Now we'll apply visualize factor analysis. And so what we do in this method is a statistical method used to model the variability in observed variables in terms of a potential lower number of unobserved latent variables. I don't think it will be good for an image data set, and as I predicted, it did not perform well in this one. We see some clusters, but they are not distinct enough. Now we'll apply and visualize autoencoders. For that, we'll install TensorFlow, and then what we'll do is we'll use some dense layers, and what we'll be doing here is we'll use autoencoder in this, and here we can see some distinct cluster but not any better than TSNE. To summarize and compare the results, we can see how different algorithms performed, out of which I feel TSNE performed the best, and well, let's move on to the tabular data and do an advanced dimensionality reduction over here. We have uh, content diabetes data set, and this is how the data looks like. We have few rows of the data set. We have different columns named as pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes degree, function, age, outcome. So this is a binary classification problem. Out, we have given some different features out of which we have to predict the outcome, one being present diabetes and zero being not present. So we if we see it is pretty balanced data set. We don't have any missing values. And let's go further and pre-process the data set, and we'll now prepare the data for dimensionality reduction. The steps include separating features and target, isolate the features, that is X, the columns that we'll use for predicting the target variable, which is Y, the Y column, and we'll begin with scaling the features, standardize the data. So mean equal to 0, we'll try to have standard deviation equal to 1 to ensure all features are on the same scale. This step is very critical in techniques like PCA and TSNE and UMAP, confirming the scale data. So we'll verify that the data is scaled or not. And as we can see, it is pretty much scaled. It is not having um, mean, and ideally the mean is almost equal to 0 and should be. And after scaling, the standard deviation is pretty much approximately to 1, as you can see. So we're done with that, and we'll start with randomized PCA, and we can see some two different clusters forming, but it is higher order dimensions. We don't have that many dimensions, but still 10 dimensions, and going to a principal component, which is a very old algorithm. I don't think it is performing very well enough. Now we'll go to applying TSNE. I hope it provides a better result. So we see some clusters forming. There are two clusters different, but still I don't feel it's good enough. Let's try to go with a UMAP. Again, we'll install the necessary library, and then we'll use the UMAP function and fit the model. And then we can see we have this cluster and this cluster, and we have some outliers over here. Now we'll be using ISO map, and the results are visible over here. Then let's go to kernel PCA. Just call the kernel PCA and call the fit function here. Let's apply incremental PCA as well in the next step. So we'll go on to visualizing factor analysis. So we have factor analysis over here, and then we'll use autoencoder. Some dense level forming, and this is how the autoencoders look like. In all, we see that PSNE perform pretty well out of all. Now let's go to Databricks and Databricks one. So what we'll be doing here is we'll be using one of the labs provided in the link. Visualization as two-dimensional Gaussian, and in the third part, we'll be doing second part we'll be doing PC projection visualization. So to begin, we have um, two-dimensional Gaussians, and in this step, we'll prepare the plot and create 2D Gaussians. So this is how it looks like, the two-dimensional Gaussian plate. And in the next step, we'll generate layout and plot the data. So here we are plotting the data. And in the next step, we'll be using we'll be interpreting PCA, and PCA can be interpreted as identifying the directions along which the data varies the most, where we have the high variance. And if we see, um, So simple covariance matrix, and we will define it as this, and in the covariance function, and then we'll be using eigen decomposition. So once we're done with that, we'll see the PCA score, and in this cell, we'll write a PCA function and evaluate PCA on sample data sets. So this is the PCA algorithm, and on data random, we'll try to use a PCA. And first, we need to convert the data random to RDD, random data RDD, and all subsequent operations on random data RDD will performed here. And then we'll be visualizing the PC projection. So this is how on the on this axis the data varies the most. So we'll be using icon decomposition on this one, and we'll generate layout and plot the data in this step, and then we'll use three-dimensional data. So this is the three-dimensional data. On this plane, the data varies the most in this plane. So we'll make use of that plane, and we'll convert the 3D data to 2D data using PCA. And in this step, we're doing that. We're calling the PCA function, and we'll visualize. So the 2D representation of 3D data looks somewhat like this. And I believe the higher variance lies over here like this. So maybe we'll be using that variance explain. So that's it for the video. I hope you learned something out of this. Have a good one.